Hello. In this lecture, we'll state Gauss' remarkable theorem, which states the following. Suppose you have two regular surfaces which are locally isometric to each other. So then their Gaussian curvature remains the same. So in order to show this thing, we'll introduce first Christoffel symbols. Yes, first we'll introduce Christoffel symbols, and using it, we'll be proving the remarkable theorem due to Gauss. So let us take a regular surface in R3. And U sigma be a surface patch for S. Okay, so now let me draw a picture. So suppose this is my surface patch. Sigma U is contained in S. And now if I take any point, so we know, so there exists a normal to this surface. And we have a tangent plane at this point. So this NP, so this is given to be equal to sigma U cross product with sigma B divided by norm of sigma U cross sigma B. So this N is normal to this tangent plane. And also we have a basis sigma U and sigma B of the tangent space TPS. Okay, so therefore, so we have these three vectors, sigma U, sigma B, and this N. So let us call it to be N bar. So we have this three vectors, sigma U, sigma B, and N bar. So they are linearly independent in R3. Okay, so sigma U, sigma B is a basis of the tangent space S, and N bar is a unit normal vector field on sigma u. Now, if I take sigma u, sigma v, n bar, so this forms a basis of R3. Okay, so these three vectors, it forms a basis of R3 because they are linearly independent. And if I take the subspace generated by these three vectors, it will be of dimension 3. So that it has to be whole of R3. So therefore, so these three vectors, it forms a basis of this R3. Okay. So now if I take sigma u, so this is again a vector in R3. So this you can write as a linear combination of sigma u, sigma b, and n bar. So this will be equal to gamma 1, 1 sigma u plus gamma 2, 1, 1 sigma b plus L1 n bar. Sigma ub is equal to gamma 1, 1, 2 sigma u plus gamma 2, 1, 2 sigma b plus L2 n bar. Sigma vu, so this will be equal to gamma 1 to 1 sigma u plus gamma 2 to 1 sigma b plus L2 bar n bar. Sigma v b, so this will be equal to gamma 1 to 2 sigma u plus gamma 2 to 2 sigma b plus L3 n bar. Okay. So this coefficients gamma I, j, k, so these are called my crystallizable symbols. The coefficients gamma k I j, where this I, j, k are either 1 or 2 are called the crystallizable symbols. So these are called the crystallizable symbols of S determined by sigma. Okay, so now since sigma ub is equal to sigma bu, so this will imply what? So this will imply gamma 1, 1, 2 is equal to gamma 1 to 1 and gamma 2, 1, 2 is equal to gamma 2 to 1. And L2, so this will be equal to L2 bar. So this two equations are same. So this will imply that the coefficients are same. So therefore, gamma 1, 1, 2 is equal to gamma 1, 2, 1. Gamma 2, 1, 2 is equal to gamma 2, 2, 1. And L2 is equal to L2 bar. Okay. Also, note that if I take n bar u, so this will be equal to some a sigma u plus b sigma b. Okay, so this already we have seen earlier. Because this n bar u, it belongs to the tangent space TPS, where this P is this point. So therefore, this n bar u, so this you can write as a linear combination of sigma u and sigma p. So let us write. So this is equal to A sigma u plus B sigma b. And similarly, n bar B is equal to C sigma u plus D sigma B. Okay. So this A, C, B, D. So this in fact it is the matrix of the linear operator D and P. And this matrix A, C, B, D. So this is equal to the following. So this already we have seen. So this is equal to inverse of this matrix E, F, F, G multiplied by L, M, M, N. So where this E, F, G are coefficients of first fundamental form, and L, M, N are coefficients of second fundamental form. Okay. So now our next goal is to find these Christoffel symbols in terms of the coefficients of the first fundamental form and second fundamental form. In order to determine the Christoffel symbols, so we take the inner product of these four equations with the tangent vectors sigma u and sigma b. Okay, so now what we will get is the following. So gamma 1, 1, 1, capital E plus gamma 2, 1, 1, capital F is equal to the inner product of sigma u u with sigma u. So this is equal to half of E u. Okay, so how we have obtained this equality? So let us see this thing. So we know that this E is equal to the inner product of sigma u with sigma u. And now if I take the partial derivative of E with respect to u, so we'll get this thing. It is inner product of sigma u with sigma u plus inner product of sigma u with sigma u. So therefore, inner product of sigma u with sigma u is equal to half of EU. Okay. And similarly, we'll get this equation also. So gamma 1 capital F plus gamma 2 G is equal to the inner product of sigma u with sigma b, which can be shown it is equal to Fu minus half of EB. Now, next equation, gamma 2 E plus gamma 2 F is equal to the inner product of sigma UB with sigma U, which is equal to half of EB. And gamma 2 F plus gamma 2 G. So this is equal to inner product of sigma UB with sigma B. So this is equal to half of GU. We'll get another two equations. So gamma 2 capital E plus gamma 2 capital F is equal to the inner product of sigma BB with sigma U, which is equal to FB minus half GU. And the last equation will get the following: gamma 1 to 2 capital F plus gamma 2 to 2 G is equal to the inner product of sigma BB with sigma B. It is equal to half of GB. Now let us pair this above equations. So if I take the first two equations, so determinant of this linear equation, so if the left hand side, if I take the determinant of EFFG, so that is equal to EG minus F square, so which is not equal to 0. So therefore, so this two equation you can solve and you can get the Christoffel symbols. Similarly, if I take the second pair of equations, here also note that, so we are getting this matrix EFFG whose determinant is EG minus F square, which is not equal to 0. So therefore, again, we can solve these equations. And similarly, for the last pair also, so in the left side, we have the matrix EFFG whose determinant is EG minus F square, and it is not equal to 0. So therefore, we can compute the Christoffel symbols. Okay, so therefore we have the following conclusion. So it is possible to solve the above system of linear equations as Eg minus f square is not equal to 0. Okay, and also note that, so if I take the Christoffel symbol gamma Kij, so it is a function of E f g and its partial derivatives. Okay, so in fact, we do not need second fundamental form right now. So gamma Kij, it is a function of EFG, and which are the coefficients of the first fundamental form and its partial derivatives. Okay. Okay. So also we can check this thing. So if I take this gamma 2 1 2 and take the partial derivative with respect to u minus gamma 2 1 1, take the partial derivative with respect to v, plus gamma 1 1 2 multiplied by gamma 2 1 1 plus gamma 2 1 2 multiplied by gamma 2 1 2 minus gamma 2 1 1 multiplied by gamma 2 2 2 minus gamma 1 1 1 multiplied by gamma 2 1 2. So this will be equal to minus E times, so Lm minus n square whole divided by Eg minus f square. Yeah, so if I try to compute this thing, so this expression left hand side, it will be equal to this product of minus E with Lm minus n square whole divided by Eg minus f square. So this in fact is the most famous equation given by Gauss. Okay, so this equation is given by Gauss. Okay, so now again, so this is equal to minus E times K. So what is K? So K equal to Lm minus n square divided by Eg minus f square. So K is the Gaussian curvature of the surface S at P. So we have this thing, and so therefore, so K is equal to the left hand side divided by this minus E if E is not equal to 0. Okay, so now suppose you have a local isometry. So local isometry, it preserves the first fundamental form. So the coefficients E, F, G, it will remain invariant under local isometry. Local isometry matrix between regular surfaces keep the coefficients of first fundamental form invariant. Okay. So from this above equation, the Gaussian curvature K remains invariant under local isometry. Okay. So let me stop with this the with the statement of uh, the remarkable theorem of Gauss. So it is also called theorema egregium. The Gaussian curvature K of a surface is invariant by local isometries. Okay, so I'll stop here today.